Okay, so we've seen how to solve a partial differential equation on a rectangular grid. And this is great if we have something that is rectangular in shape, but in most practical situations this isn't the case. In fact, most problems you don't have such simple geometry. There's light at the end of the tunnel, however, and although it adds to the complexity, irregular shapes can be added to the finite difference method. Okay, so we're going to look at a parametric method that assigns alpha and beta terms around the node of interest, and we're going to be looking at a Dirichlet boundary condition. So let's sketch this up. Say we have an irregular boundary that looks something like this, and we have a grid that is attached to the boundary that looks something like this, and we are interested in calculating the value at node ij. So ij, I'm just going to go ahead and label the other nodes. So that's I plus 1, I minus 1, this is j minus 1, j plus 1. Okay, so the difference between j plus 1 and j is delta y, and the difference between I plus 1 and I is delta x. Okay, now the difference between I and I minus 1 is not equal to delta x, but we could say that it's equal to some factor of it. So let's say alpha 1 times delta x. Okay, and just for simplicity's sake, I'm going to add alpha 2 in front of this delta x. We could do the same for the y. So j and j minus 1 is beta 1 delta y and beta 2 delta y. In this instance, alpha 2 equals beta 2, which is equal to 1. Okay, so how do we solve our second derivative? Well, the second derivative is given by this form, which is really just the derivative with respect to x of a derivative of phi with respect to x. So if we know what the derivative of phi is with respect to x, we can apply this form of the equation to come up with new parametric forms. So let's look at the forward difference, that is day phi by day x at I minus 1 j is equal to phi ij minus phi I minus 1 j divided by alpha 1 times delta x. And the same for day phi by day x in the backward difference, that is I plus 1 j is equal to phi I plus 1 j minus phi ij divided by alpha 2 delta x. And if we plug these two terms back into our original equation, what the second derivative is, we can get the following. So that is day squared phi by day x squared is equal to 1 over x squared delta x squared multiplied by phi I minus 1 j minus phi ij over alpha 1 times alpha 1 plus alpha 2, and we have the addition of phi I plus 1 comma j minus phi ij divided by alpha 2 times alpha 1 plus alpha 2. And similarly for in the y direction, day phi by day y squared is 1 over delta y squared. Here we have phi of I j minus 1, phi ij, subtract the 2, beta 1 times beta 1 plus beta 2, plus phi of I j plus 1 minus phi ij of beta 2 plus multiplied by beta 1 and beta 2. Okay, so now we've looked at the Dirichlet boundary condition, and we can use those previous terms to update our Laplace operator for nodes adjacent to the irregular boundary. And just to note that we could also apply this for derivative boundary conditions.